Hi, everybody.
Hi.
A couple of you have asked how to do a problem like this. So in the notes, I talk about a formula called percent composition. And so that's in the chapter 3 notes is where you'll find that. And basically, that's what this problem is. All right. And so I wanted to walk through how I would approach solving this, which I think is probably a little less confusing than the explanation provided here. So the formula that I gave you in the lecture notes for percent composition, like if we just, as an example, we'll just work through carbon, but the same formula applies to any element in a given compound. So the percent composition is equal to the mass of that element, so the total mass of that element in the compound, divided by the total molecular weight, which you'll remember we also call that molar mass, formula weight, I don't know, a bunch of things. Okay. All those mean the same thing. It's the total mass of the compound based on adding each atom in it together. And then because it's a percentage, that fraction has to be multiplied by 100%. So the general rule that I give you is that this is part divided by the whole. Okay, so here for carbon it's 44.77% is given to us right there, and we're also given the total molecular weight. And so we'll just plug it into the formula. We need to understand that there might be more than one carbon though. Each carbon weighs 12.01 grams per mole. That's from the periodic table. But the total number of them is a mystery. That's kind of what we're trying to figure out here.
How
Okay.
can you define a mystery though? That's my question.
That's everyone's question. All right, and your total molecular weight is given here. Molar mass, molecular weight, they mean the same thing, so we'll put that one in here. And of course, we can't forget that that is also multiplied by 100%. So from here, it's just algebra, right? And so let's get rid of the percentage first. So that didn't change anything in our fraction at all. I do want to point out that you have formula weight on top and a formula weight on the bottom. So these units are just going to cancel each other. I'm going to stop writing them now. So we're just going to get a number with no unit, which makes sense because remember that we define X as the number of carbon in the compound. All right. And so then to solve this, we will next multiply by 134.13. Oh, we canceled that unit. So that way now I don't even have a fraction anymore. So on the left-hand side, we end up with 60.05, and on the right-hand side, we end up with X times 12.01. To solve that, we'll divide by 12.01. And so, as it turns out, X equals 5. Okay. The way that the explanation is structured, it'll get you to the same answer. I just think it's less direct. So I'll explain the way that they're trying to approach this here. They're making a ratio from the percentage because they're saying, okay, so if we had 100 grams of this compound, then 100 times 44.77 is 44.7 grams. That's where they got this number from. Okay. And so, and you can always think of fractions. It's a good idea to think of percentages that way. They're really a fraction, right? Oh, I can't write on that. So 44.77% is the same thing as 44.77 out of 100. And in this case, this would be grams of carbon and grams total. All right, and so that's the logic there. And so that's where they got these numbers from. It's from their percentages. And then they're saying, all right, well, if you take the total amount of carbon and divide it by how much each carbon weighs, you'll get a relative ratio compared to the rest of the other elements in the rest of the compound. All right, and so they do that. And then they're just comparing with how much oxygen there is. There's not a real good reason for that. You could choose any of the elements to be your basis of comparison. You know, a lot of the time it's easier to choose the littlest one. It makes the math a little bit more direct. So to figure out a mole ratio, which is something that's going to come up when we talk about gases. So mole ratio is just kind of the inside part of the calculation. In this case, this is not an X, by the way. This is a chi. This is the Greek symbol. It looks like a capital X, but it's not. So the part due to the carbon divided by the whole. In this case, we're talking about mass, right? So to be the mass of the carbon divided by the total. All right, and so that's what they're looking at here. But you can do molecular, you know, you can use moles, you can use molecules, you can use whatever proportionality you want here, as long as the units on the top and bottom are the same. In this case, they chose to use grams, and so they pick oxygen as the basis for everything. And so you just divide everybody by the 2.982 that we found from the mass of oxygen conversion. By the way, this part might make more sense to you guys if I write that the way that we've been practicing, which is, so going back to carbon again, they wrote 44.77 grams. If we wanted to figure out how many moles that is, not now, we would go 1 mole per 12.01 grams, right? So that's what they're doing. That's where the numbers are coming from. They're just not showing it as dimensional analysis, but that's the way we've been working on it. So maybe that makes a little more sense that way. All right, and so they did that for each one of them to get the relative number of moles, and then they take it and find whichever one is the lowest. Okay, stop. Whichever one is the lowest, and they divide them all. All right, and that gives you what we call the ratio. All right, mole ratio is this number and this number. All right, and so when you compare your mole ratios, you can't make a chemical formula out of these because they're not whole numbers. You have to have whole numbers to write a chemical formula. You can't put C 1.25, H 2.5, and O 1.0, right? You can't do that. So the reason they multiply by 4 is it's the smallest whole number that'll make all of these work out into a whole. So 1.25, and the reason they pick that is because of this. This is 1/4, right? It's 1 1/4. But the fraction, the part that's annoying, is this. So to make it not annoying, we have to multiply that by 4. And when you go 1.25 times 4, you get 5, which is exactly what we got doing it the other way. So there are so many ways to solve these problems. This is just 2 methods, right? But we had some confusion about, like, where does this 4 come from? It just seems like it comes out of nowhere. It's because we look at the fractions, and you'll see that that's not the only fraction. 2.5 is also a fraction. But if you multiply that by 4, you're going to get a whole number as well, right? 0.5 times 4 is 2, plus that 2 there. So you're going to get 4. All right, and so that's how they set this problem up. You can do it any way you want, so long as you get whole number ratios out of it. Okay, hopefully that helps. But if not, as always, feel free to ask questions.